Hello everyone, my name is Weiyu Huang. Today, I'll talk to you about our recent work in network comparison, where we try to define a network distance in the space of networks and use persistent homology as a tight approximation of that. To start, let's consider we live in an era of network data. Examples of network data include internet, online social media, and grid analytics. In internet, each node represents a site, and the connection between two sites represents the existence of hyperlink between them. In online social media, each node represents a user, and the existence of a connection between them represents that these two users may be friends. In grid analytics, each node represents an energy producer or energy consumer, and the connection means there is an energy transmission from the energy producer to energy consumer. In all these examples, network data structures try to encode relationship between elements in a network. This model has been studied extensively. However, the question of our interest is how do we evaluate the dissimilarities between networks? This question has been studied by many researchers before, and because we want to evaluate the difference between networks of arbitrary number of nodes, therefore, most of the existing approaches use global feature heuristics. For example, moments of centrality measures, motifs, or spectral properties. Such approaches have two main drawbacks. Firstly, it only uses partial information of the network. Therefore, one method applies well for one application may not work well for the other application. Therefore, the method tends to be highly application dependent. Another problem these approaches have is it may have conflicting judgment. For example, we may have network A and B to be highly similar, network B and C to be highly similar, but on the same hand, network A and C are very different from each other. This is because the triangle inequality is violated. Motivated by this, we want to define and estimate distances in the space of networks. This is more generalizable compared to the feature heuristics. It is also more universal, and because valid matrix satisfies triangle inequality, the conflicting statement is not going to happen. Besides the relationship between a pair of nodes, we also want to consider high-order networks, and therefore high-order relationship between 3 nodes and 4 nodes. We have 2 examples of why such consideration is meaningful. In collaboration networks, we have the collaborations between 3 researchers and the collaborations between 4 researchers. This is not the same as the collaborations between only 2 researchers. In knowledge graph representation, the association between 3 things, for example, image, location, and online social media, is not the same as the association between 2 things, for example, image and location. Therefore, we want to consider high-order networks and evaluate the distances in the space of high-order networks. Formally, we consider high-order networks as a tuple, where we have the node set and a bunch of relationship functions. The relationship function of order k is the mapping from the k+1 tuple to the non-negative real numbers. This measures the relationship between these k+1 elements in the X. We have one requirement, that is the relationship between A and B should be the same as the relationship between A and B, since they measure the same amount of information. Also, when the network represents proximity or similarity, then the relationship is going to be order decreasing. This means if we add a new node in the existing set, the relationship is going to decreasing. To see this, if we consider proximity between A and B, and the proximity between A and B and C, then the proximity between A and B and C should be no greater than the proximity between A and B. When the network represents dissimilarity, it should be the other way around, and we should have the order increasing property, which means the dissimilarity between A and B and C should be no smaller than the dissimilarity between A and B. Since we want to consider the comparison between networks of arbitrary sizes, we may need a way to map the nodes in this arbitrary number of nodes. A mathematical tool called correspondence is very handful. Formally, a correspondence between two node sets is a subset of their Cartesian product, such that every node in X has a mapping in Y, and similarly, every node in Y has a mapping in X. As example here, we have 3 nodes in X and 4 nodes in Y. X1 is mapped to Y1, X2 is mapped to Y2, and X3 is mapped to both Y3 and Y4. This means each node in X has at least one node in Y, and each node in Y has at least one node in X. This is a generalization of permutation. Given one pair of networks, X and Y, and the correspondence, we can define the network difference between these two networks, measured by the correspondence as the bottleneck tuple, such that the respective relationship in the two networks is maximized. Then we can define the proximity network distance as the minimum of such network distance that is taken the minimum by some correspondence C. Therefore, we can show that this is a valid metric in the space of high-order networks. As application, we consider the collaboration networks constructed from publications of two famous researchers in signal processing, Professor Martin Vitali and Professor Georgian Giannakis. We consider their publication in transaction signal processing and construct this kind of networks for 5-year domain or 2-year domain for Professor Georgian Giannakis. We found that the tool we have been developing successfully identified the networks of Martin Vitali from those of Professor Georgian Giannakis, even though the latter may have 2-year network and 5-year network. This is the multidimensional scaling of the result, and we see the network from Martin Vitali, the red nodes, is different from the networks of Georgian Giannakis, which are either the black one or the blue one, depending on whether it's 2-year or 5-year network. The network metric is a very useful tool. However, because we need to consider all the correspondences, it's very hard to evaluate when the networks are large. Therefore, we want some computationally efficient tools that can be generalizable to large number of nodes. To do that, we consider simplicial complex, and in the next few minutes, I'm going to give you an introduction to computational topology. The building block in topology is called simplex, where the k simplex is the convex hull of the set of points. The 0 simplex is a vertex, a 1 simplex is an edge, a 2 simplex is a triangle, and a 3 simplex is a tetrahedron. With simplexes, we can define simplicial complex as the collection of simplexes that are glued together. There's one important concept for simplicial complex, which is homology. It tries to describe holes that do not have interiors. You may consider, why do we want to ask this question? Well, we can think of rubber bands. We have 3 rubber bands in a 2-dimensional plane. There's a hole in the 2-dimensional plane, and the red rubber band encloses this hole. The blue one and the green one doesn't enclose this hole. You can imagine yourself move these rubber bands arbitrarily. However, you cannot leave them from the plane. Then no matter how you move them, the red one is always going to enclose the hole, and the blue one and the green one is always not going to enclose the hole. Therefore, we want to find a difference between the red rubber bands compared to those between the blue and the green rubber bands. And this can be done by homological feature, which tries to formalize the notion of holes that do not have interiors. As example, we have AB, BD, DA. They form a hole, but this is not a homological feature because the interior ABD exists. On the other hand, we have DC, CD, and DB. They form another hole, and because there's no interior, this is a homological feature. More examples coming up. We have one homological feature here, one feature here, 2 features here, and 1 feature here. The simplicial complex and homology is interesting, but there's no way for us to incorporate weights. To solve these problems, we can consider there's an underlying domain that is called time, and we can assign each simplex in the simplicial complex a value represents the time point when the simplex appears. In the example we have here, the 4 zero vertices appear at time 0, And therefore, at time t equals 0, we have 4 vertices. At time t equals 0.1, we have the edge between A and B. Time t equals 2, the edge between B and C, etc. This kind of inclusion of simplices continue to happen until we have everything in the simplicial complex added to this filtration. The persistent homology is then defined as the holes without the interiors for this filtration of simplicial complexes. To be more specific, at time t equals 0, we don't have any holes. Still the same, no holes at time t equals 0.3. At time t equals 0.5, we have one hole formed by AB, BC, CD, and DA. On the right, we have a persistent diagram. The horizontal axis denotes the birth time of homological feature, and the vertical axis denotes the death time of homological feature. Because we know there's one homological feature born at 0.5, we represent this as a dashed line. At 0.7, there's another hole formed by this AB, BD, DA. Therefore, we have another horizontal axis that is going to be 0.7. At 0.8, the hole that is formed at 0.7 becomes filled with the interior ABD, and this homological feature no longer exists. This represents to the point 0.7, 0.8, which means there is a homological feature between 0.7 and 0.8. Also, since 0.8 is the last point we have of simplex added to the filtration, this means the holes that are born at 0.5 is going to stay there forever. We represent this as 0.5 infinity. The next question we want to ask is, maybe if we define the difference between persistent diagram, this can be used as an approximation of the network distances. We first consider a scenario where the persistent diagram have the same number of points. This is relatively easy to consider their difference. We can just try to find the best matching between these points and assign the difference between the persistent diagram as the bottleneck that is not matched well by this best matching. In this example here, 0.5 infinity is going to be matched to 0.5 infinity, 0.7 infinity is going to be matched to 0.7, 0.8. And the difference between the persistent diagram is going to be the bottleneck of the maximum of the birth time and the death time, which is going to be infinity in this case. When the persistent diagram have different number of nodes, one way to do that is we can assume there are a number of homological features that are born and die at the same time for the persistent diagram with the smaller number of points. And therefore, for any points in the persistent diagram with higher cardinality, it can be either mapped to the existing point in the persistent diagram, or it will be matched to a diagonal point in the other persistent diagram. In this example, 0.5 infinity is going to be matched to each other. 0.7, 0.8 is going to be matched to 0.75 and 0.75. Therefore, we have the persistent diagram difference as 0.05. The central theorem in our paper is that the persistent diagram, their difference, can serve as an approximation, actually a lower bound of the network distance. Moreover, if the network is constructed nicely, then there's nothing lost when we consider the persistent diagram. And there are lots of examples that the lower bound between the persistent diagram difference is the same as the actual network distance. We consider this in the classification of collaboration networks. We construct the networks from engineering community and mathematics communities. To do that, we consider all the others publish their work in some journals in engineering. For example, signal processing, automatic control, wireless communication. We do the same thing for mathematics and evaluate the persistent diagram difference between the corresponding networks. We found this lower bound actually can distinguish the networks quite well. Especially, we have some networks that are constructed from the same journal, for example, transaction of signal processing, but for different time domains. They are actually highly similar in these lower bounds. We also try a more challenging task, which is we try to distinguish engineering communities with different research interests: automatic control, signal processing, wireless communication. And we found these tools give us a moderate success in distinguishing such problems. So I hope in the past 15 minutes, I have given you a very introductory point of view about our recent work in network comparison. We try to define a valid network distance in the space of high-order networks. This can be served as a proper measure of dissimilarity, which will overcome some of the main drawbacks of existing approaches. We then use persistent homology and try to define this for networks. This is a very elegant mathematical tool that can be efficiently evaluated. We examine holes and boundaries, and this would provide a tight approximation of the network distances. We then apply these tools to successfully distinguishing research community with different interests, for example, engineering versus mathematics, or different research communities in engineering. Thanks very much for your attention.